So just to review from last time, this was the Stirling engine. If you want to see it in operation, go find the L8 video. Anyway, the last one we had. And then treating the state variables table kind of like a Sudoku puzzle. You've got to have some measurements of your engine. And that's why for automobiles, they talk about displacement. So like a 5-liter engine or a 3-liter engine, that's the displacement that all the cylinders displace. And then one value that's not really advertised, I don't know why, it's just as important, it's the compression ratio. So as you compress that cylinder, you compress all the gases and then you light them. That's another critical piece of the parameters. Once you have compression ratio and the displacement, then you can find the whole V row of your engine. So you can find VA, B, C, and D of that engine. You have to make some assumptions, and so in our Stirling engine, we're assuming that the coldest and lowest pressure spot on the curve was 1 atmosphere and room temperature. And then we have only one more variable that we need to assume or measure to allow us to fill out the whole table. So once we get the hot temperature, then we're off to the races. And so that's what I wanted to measure between last lecture and now. As I ran the Stirling engine for a little while in my office, then blew out the flame and touched the thermocouple to the glass. And it, like I said, the maximum temperature it got to, it was jumping around, but the highest one I saw was 180 C. And so then I was able to fill out the whole Stirling engine state variables table. So this is it here. And I've put this spreadsheet up on Blackboard. You can see the one for the Stirling engine that we did in class. And then I have one that's blank. It has a lot of squares that are blank for you to fill out and practice. And so if you started with this and you just had 1 atmosphere and room temperature and the volumes, VA and VC, and then the hot temperature, could you do the whole screen? Could you do all of those equations? That's going to be the calculation part of the test, is to be able to do the state variables table and then all of the work and heat calculations and the efficiency calculations for an engine. And so practice, there's 2 examples on the homework, and then you have the spreadsheet. And so you can change the numbers and make up your own problem, and then you'll have the answers there in the spreadsheet. And so you can just make sure that you understand how to do them so you can drill against your own spreadsheet. And I think that's a really good practice to be able to use a spreadsheet to kind of generate all of those formulas, and then you can check your work against your own spreadsheet. So let's walk through this problem. Also, I put the arrow diagram on here. You'll see that in these cycle problems, all the ones that we cover are going to be clockwise. So they're going to go A, B, C, D, and reset. So when you see this, if that arrow was not there, then you would assume a clockwise motor anyway. So that's what a clockwise motion in this particular PV diagram would be, a heat engine where you take in heat and you generate work. But you could run it backwards. Now, what would happen if you ran it backwards? You would be putting in work and moving heat. And that's what we do for refrigeration and heating. So that's a heat pump. So a heat pump, we put in work and we move heat from the cold side to the hot side. We run it against itself. And so to generate work, we take heat from the hot and move it to the cold, and we get work out. But if we run this backwards, it takes work and is converting that work into heat and moving heat from the cold to the hot. It's making the cold and hot further apart, or trying to. So it's pumping that heat. So that would be a heat engine, but we're dealing with a heat engine, not a heat pump. And so we're wanting to get work out, and we want to put in heat. Once we've filled out the state variables table, then we can start working on these performance parameters. And so notice there are already some zeros here. So help me understand why the energy change for leg A, B, so from point A to point B, is 0. How can I can just automatically put that without doing any calculations? All right, we'll hold off on that. What about the work? What about BC? Can you understand this 0 here for leg BC? So from going from B to C, I'm saying there's no work done. How can I know that? Look at the state variables table. Point B and point C. What's the work depend upon? Here's the equation for work. One of the equations for work.
There's no change in volume.
Right, no change in volume. So the log of 1 is 0, so I'm going to get 0 work. Plus, if you think about it, there's no change in volume, so there's no expansion or compression. So there's no work done by the system and no work done on the system. So if there's no change in volume, there's no expansion or compression work. And so the same for D to A. No change in volume, so work is 0. So you can already fill out some of the performance values just looking at the state variables table and knowing, or looking at the PV diagram. You can see that this is an isocore here, so there's no work there and no work there. Let's use this equation here, though, the work equation, and compute the amount of work done for leg AB. So let's do a couple of these on the board. 3. Just make sure I've got it So the number of moles we have up there at the top, 0.0002174. We have the gas constant, the temperature. So what's the temperature for the AB leg? This is isothermal reversible expansion. Say it louder, please.
Same temperature is 453.
453 Kelvin. And that's all pretty straightforward. The real trick is making sure you get the volumes in the right spot. So it's V final on top. So we're going from A to B. So B is V final. Can you read that for me? 005316.
Yeah.
Liters. And then VA.
0.002375.
75 liters. And so that's the work for leg AB. And it ends up being 0.660 joules. So the moles cancel, that's another thing. Always check your units. The liters cancel each other, so your argument for the logarithm is unitless. That's a good requirement. And then we're left with joules. So it's negative 0.66 joules. So what does that tell us? That tells us that the system did work on the surroundings when it expanded. And that makes sense. Now, if we do the same equation for CD, then we have the big volume on bottom, the small volume on top, and we have a different temperature. It's the same number of moles. But because it's a lower temperature, it's a smaller number. Okay? And so we end up with, for CD, same calculation, but we end up with a positive 434. Now, where'd this negative sign go? When we flip this ratio, we have the log of a number that's less than 1, so it's negative. And so this log result is negative, that cancels the negative sign, and we end up with a positive work value because we're compressing the gas. So we're doing work on the system by compressing it. So that's what I call resetting the system. We compress it back to its small volume, and we have to do work on the system, the working fluid. And that resets it. So now when we heat it up, it can do work on the surroundings at a higher temperature, and it does more work at a higher temperature than it takes us to reset it at a low temperature. So that's how the heat engine works. It allows us to work between these two volumes, but if we do that work at different temperatures, then we get a net result. Okay, let's do the energy. We kind of had trouble with that one. Here's the equation for energy. That's why I put it off, because these are in order. And so there's the internal energy equation. And you see that it's just the heat capacity at constant volume times the change in temperatures. So that tells you why there's zero energy change for leg A to B, because it's isothermal. And the same thing for C to D, it's isothermal. So for those isothermal legs, there's no change in internal energy. So we could write those zeros in right away. Let's go ahead and do the calculation for leg BC. So this, we cool it down at the constant volume, going from B to C. So let's delta U, BC, and that's equal to negative N. Well, the equation's on the board. I'll go ahead and put in the numbers. 0.00002174 moles. Oh, we've got to compute CV. Okay, so I've got a number there, but where did that number come from? We've got a Stirling engine, and we didn't have to insert any special gas in there. So what do you think the gas is inside that Stirling engine? Atmospheric gases, and it's composed of what? What are the major components of atmospheric gases? Nitrogen, oxygen, carbon dioxide. All three of those are linear. Okay. So we have translational modes of degrees of freedom, and we have rotational degrees of freedom, and we're not going to have any active vibrations because we're not at hot enough temperature. So we can just treat atmospheric gases, even though they're different species, nitrogen, oxygen, CO2, as a linear working fluid. So we would have this CV is 5 halves R. We have 3 halves R for the translations and another 2 halves for the 2 rotations. Because it's linear, it only has 2 rotational degrees of freedom. So that would be CV, 5 halves R. Go ahead and calculating that, we get 20.785 joules per mole Kelvin. So here, the CV linear is 20.785. And we're going from B to C, we're dropping in temperature, so the final temperature is the cold temperature, 298. And the hot temperature is 453. And so this is going to be a negative sign. And so, is that right? Yeah, T final is cold. Yeah, so that'll be a negative sign, and it'll cancel this. Doesn't seem to work out.
It doesn't cancel because of negative.
Say that again.
It shouldn't cancel because of negative at the beginning.
This one here.
Yeah. So go to positive.
Yeah, to go to positive, but we're cooling it. So we're cooling the system, so the system should lose energy. So I'll need to check this equation up here. So U, delta U is equal to Q plus W. And in this case, W is 0. So it's equal to Q. And Q is, I think this negative sign is not supposed to be there. So forgive me on that negative sign, because what we have, and again, this is why you do this analysis and say, does it make sense? We cooled the system down. The system has to have a drop in energy. It's negative. Its delta U has to be negative. We cooled it down. And so that's telling me that that negative sign should not be there. Okay. Apologize. So we have this negative 0.7 when you do the put these numbers into the calculator. And so that's going to be 0.7 joules lost when we cool it down from 453 to 298. Then we do the same kind of calculation again, C to D. We've got, it's an isotherm, and so there's zero change in energy. And then D to A, even though it's a larger change, you look at the PV plot, it's a larger change in pressure, but it's still the same temperature change. And so we're just going to have this same calculation with 453 and 298 swapped. Okay, and a plus sign here. And so that's going to be the same value but opposite sign. So that one will be positive. And so we have plus 0.7. So our delta U is just based on temperature. We cool it down. The system loses 0.7 joules. We warm it back up. The system gains 0.7 joules. So the real effect for our heat engine is the two isotherms being at different temperatures. Do you see that? Yeah. Now, let's go ahead and calculate the heat. This equation up here, the delta U is Q plus W. We could solve for Q, which is delta U minus W. And so that's pretty easy to do. We just take the delta U column and subtract the work column. So 0 minus a negative 0.66 gives us a positive 0.66. A negative 0.7 minus 0 is still negative 0.7. 0 minus 0.434 is negative 0.434. And then 0.7 minus 0 is 0.7. So those are all of the heat values for each leg. And so for the isotherms, the internal energy doesn't change. And so in order to do that work, we're putting in heat. We put in heat, and to maintain that temperature on expansion, we put in heat and we get that much work out. Yes?
So for the two isotherms, should we expect them to be the same value, just different times? Or is that just for this example?
You mean the heat and the work should be the same value, different signs?
Oh, no, for delta U.
Oh, for these?
No, just the row of the delta E. You see how like BC is the negative of AD?
Yes. Since you're just doing isothermal changes, the internal energy will be, you went down in temperature, so that would be the negative 0.7, and you went back up in temperature, it would be the same magnitude, different sign.
Okay.
Yeah, because the only thing that delta U depends upon is temperature. Yeah. All right. And so then, now that we have the heat values and we have the work values, we can figure out what our efficiency is. Because we can take the net amount of work generated by the cycle and divide that by the heat that went into the system. Okay. So this is our efficiency. It's that net amount of work. When I say net, I mean you just add up the work column. So it did some work, it had some work done on it. What's the net result? How much work did we really gain from the system? And so it's negative 0.226 joules. That's how much work came out of our engine per revolution. Okay. And so that's not very much, okay? But again, it's per revolution. If you get 1,000 revolutions per minute, then you get a measurable amount of work out of it. And then the total heat in. This is where people make mistakes. They think that it's net work divided by net heat, which would always give 100% efficiency. Okay. But you have just the positive values here. This is what you put into the system up here to do that expansion, and this is what you put in the system to heat it back up, reset the temperature. So 0.7 and 0.66 is going to be the 0.136 here. So that's the amount of money you had to spend to get this thing to go around one revolution. You had to put that energy in. That was our alcohol flame. So we took that alcohol, that resource, and consumed it in order to introduce heat into the system, and then we got work out and made our little LED light up. And so that gives us an efficiency of 0.166. Not the greatest. It tells you why we don't drive down the road with our Stirling engines. Okay. Now that's just this particular Stirling engine with this particular temperature and these volumes. There might be some configurations where you could make it a little more efficient. In fact, that's what's fun in the spreadsheet. You can go in there and play with the volumes, and you can play with the temperatures, and you can see what kind of efficiency you can get out of the Stirling engine. Now that we have all of the equations built in, then you can play around with the values. Okay, now the Carnot cycle would be a more efficient version of a heat engine. And instead of isocores, the Carnot cycle has adiabatic expansion here and an adiabatic expansion here. So it's a reversible process. And so for Carnot efficiency, it's just a function of the hot and cold temperatures. It's the most efficient engine that you can get. So with these two temperatures, 298 and 453, those temperatures would give an efficiency of 0.342, so 34% efficient if this were a Carnot cycle. So, it's more than twice as efficient as a Stirling engine. Just really have difficulty constructing a purely well-done Carnot cycle, but that would be the maximum efficiency you could get out of these two temperatures. So it's always good to compare whatever heat engine you have to a Carnot cycle with those temperatures, just to see how close to ideal you are. Let me pause here because this is a good stopping point. Are there any questions, things that you need to clarify? Okay, seeing none, let's move on to the Carnot cycle and talk about these adiabatic expansions. So now we can construct a heat engine that has all reversible processes. So we don't have any isotherms. Well, you do have isotherms. We don't have any isobars or isocores. We don't have any straight lines across pressure or straight vertical lines in volume. We have these curved lines that are reversible processes. So we can go, following that most efficient expansion along the isothermal line, and then also the adiabatic expansion. Trying to decide which is which, the adiabats are more steep in a PV diagram than the isotherms. And so when you're looking at four curves on a graph, you've got to know which is which. And so this is the first thing to do, is to look at the curves on your graph and be able to identify which ones are isothermal and which ones are adiabatic. Isothermal expansion, you can just look at the final pressure based on the initial pressure and this ratio of volumes. And so that's going to give us this slope here, the isothermal slope. And then the adiabatic, there's no heat flow, so there's a temperature drop. And it looks like the same slope, but you have this exponent here. And that exponent is always greater than 1, which means that it's a steeper slope. Okay. And so then V final is always greater than V initial for expansion. And so this is a fraction, it's less than 1, but then gamma is greater than 1. So it drops steeper. We'll see this next in the full cycle in a little bit. Let's talk about how we calculate that V final. Because in this case, all three variables are changing, pressure, temperature, and volume, and we just have a two-dimensional plot, pressure and volume, we need to know what temperature it's going to hit and what that volume is going to be. So a lot of times we're given the temperatures in a Carnot cycle, but we're not given the volumes. Or we're given the volumes and not the pressures. So we have two of the variables, we need to solve for the third. And so that's when we use this gamma. This gamma depends upon the type of gas that we have, because gamma is this ratio of Cp over Cv. And since Cp is equal to Cv plus R, this is always greater than 1. We can tell how much energy change there's taking place because we know the temperature change. So this equation's understandable from what we just did. But the ratios of volumes and temperatures and pressures need to incorporate this gamma. Now, you've got to be pretty good at this working with exponents. So look at this. This is our first example. If I've got, let's say I've got two pressures and a volume, and I want to solve for a V final. That's kind of inconvenient, being down here in the denominator when I've got this exponent up here. So how would I get the exponent to be on the other side? So let's pretend that gamma was 2, and this was Vi over Vf squared. Take the square root of both sides, okay? So instead of the square root, I'm taking the gamma root of both sides. Essentially, the square root is to the power of 1/2. And so it's just whatever that is. I'm going to take this side and multiply, raise it to the power of 1 over gamma. Do you see how that works? And then these exponents are multiplied by each other and they cancel out. But I can't do it to one side, I got to do it to both. And so this would be 1 over gamma. And so now I've got V initial and V final without any exponents, and I've got the exponents over here on P final and P initial. And so you've got to be able to look at all of those relationships. And if you don't have the relationship you need to be able to derive the one that you need. Okay? And they're all derived in the notes. You can see them in the notes. But I would like for you to be comfortable with working with your exponents. So let's look at some of those. First, let's figure out where this gamma thing came from. So now we have our 3D phase diagram. And we've got pressure and volume, which is what our typical two-dimensional plot looks like. So we're normally sitting outside this pane looking in to this complex surface. And temperature comes out of the plane towards us. And it's a slope. It's a three-dimensional surface, and an isotherm does not go down the steepest descent. An isotherm is a particular temperature. So it's a slice of temperature that cuts through this surface. Can everybody see that? If I pick a temperature and I slice that three-dimensional surface, I have an isotherm. But that's not the steepest path down that hill. It's just a slice at a given temperature. In fact, to keep it from going downhill, I have to put in energy to keep it at that temperature. So heat has to go in and work is coming out, and as I do isothermal expansion, the volume's changing, the pressure is dropping, but the temperature's not changing because I'm pumping in heat. And that's what's keeping the system from going down the steepest descent, because I'm putting in heat. But if I'm in an adiabatic situation, there's no heat going in. And so when it expands, the pressure drops faster. It's a steeper descent in pressure as I expand the gas. And so that's why the adiabats are steeper. They roll downhill the steepest way versus the expansion at a constant temperature. So in this case, Q is flowing into the system. In this case, Q is equal to 0. So because we're putting in heat at an isothermal expansion, it stays at a higher pressure. If we don't have that heat, then the pressure really drops. If we take this setup and do integration on both sides, we can integrate the energy portion with respect to temperature and integrate the work portion with respect to volume. And so we end up with dt over T, which is the natural log of temperature, and dV over V, which is the natural log of volume. And on the left, we have the number of moles times the heat capacity constant volume, and on the right, we have number of moles times R. We can cancel the number of moles from both sides, and we know that Cp is equal to Cv plus R. So R is just the difference between those two. So that's where we get this R has become this, and the ends canceled. And so then I can move this Cv over to the other side. I can divide both pieces by that. And so I have Cp over Cv minus Cv over Cv. So this is 1, and this is gamma. So I have gamma minus 1, and I have the logs. And this right here can move over to be an exponent. And I can get rid of the logs on both sides. So that's where that relationship between temperature and volume comes from, is that gamma minus 1 as the exponent. You could do the same thing for pressure and volume, pressure and temperature, Or you could just take this relationship and insert, instead of volume, you could insert temperature over pressure, and then work with your exponents to get all the temperatures on one side. So let's do a few of those. So I have this relationship up here, and let's say instead of temperature, I wanted to get to pressure. And so I could put in the ideal gas law for temperature A. I can have PA VA over NAR. And that's just an ideal gas substitution. And so then simplifying things, the number of moles hasn't changed, so that's gone. R is a gas constant, so it's constant, doesn't change. So I could take, instead of TA and TB up here, I could have PA VA over PB VB. And so I have this situation. Now how do I get all my volumes on one side? Well, I just multiply this side by VB over VA, and that would cancel those things out. And now I have VB over VA to the gamma minus 1 times VB VA to the plus 1. And so I have gamma minus 1 plus 1, so I just end up with gamma. And pressure's on the other side. Let me go ahead and, I'm going to do something to an equation. I got to do it to both sides. VB and VA. And so now VA cancels here, and VB cancels there. And so now I have a relationship between pressure and volume. I started with temperature and volume. And so you can do this with all of the different combinations of state variables: pressure, temperature, and volume. Why is this necessary? Well, we'll see in just a second. This is critical for filling out the state variables table. Okay, because remember we have the Sudoku puzzle. You've got certain temperatures, you've got maybe one volume here and a pressure there, and you've got to figure out how to fill in all of those other squares. And for a Carnot cycle, you have to deal with the adiabatic expansions. You don't have to do this for the Stirling engine, because the Stirling engine doesn't have adiabatic expansions. These are the adiabatic relationships that you need to fill out the state variables table. Let's focus on gamma for a little bit. So because gamma is required for these adiabatic relationships, this is where the identity of the gas comes in, the type of gas. Is it a monatomic gas like helium? You have the Cp over Cv. So Cv for helium is just 3/2 R. All you have is translation. And Cp is 5/2 R, because you have one more R unit in there. Okay, so that's 5/2 over 3/2, or 5/3. The R's cancel. And so gamma is 1.67 for helium. I'll pause. Anybody get a little brain spark on the CP? That's where it typically throws people. They see 5/2 and they think linear molecule, and helium's not linear, but that's CP. It's Cv plus R. So it's 3/2 plus 2/2 gives you 5/2. Let's do CO2, a linear molecule. So we start out with Cv. Always do that first. So for a linear molecule, what do you have? 3/2 for translation, 2/2 for rotation. So that's a total of 5/2 for Cv. Add 2 more halves to get to the Cp. So that's 7/2. And so the R's cancel, the halves cancel, you end up with 7/5 for gamma for a linear molecule. So the adiabatic relationships depend upon whether it's a linear molecule, a monatomic gas, a nonlinear molecule. And so this is going to be 1.4 for something like CO2, or for our Stirling engine. Even though we didn't need gamma, we could calculate it for air. You have nitrogen, oxygen, CO2, all 3 linear molecules. So for atmospheric gases, it would be 1.4 would be gamma. And that's what the adiabatic relationships would be like. And then finally, for water or any nonlinear molecule, start with Cv. You have 3/2 R for translation, another 3/2 for rotation. So that's 6. You add 2 more for Cp, that'd be 8. And so it would be 8/6 or 4/3 or 1.33 for a nonlinear molecule. And then you would use those gammas in these relationships in the upper right. There I've got temperature and volume related to each other, or volume with temperature inside the exponents or pressure with volume inside the exponent. Yes?
So do better fuels have higher gamma values?
For heat engines, the higher the gamma, the steeper the slope. And so you're going to get more work out of that adiabat. So I would, at this point, just the top of my head, I would say yes, a higher gamma value gives you more work on an adiabat. And so helium would be better than a nonlinear molecule because it has a higher gamma. It would deliver more work in that expansion. And we do kind of see that too, the smaller the atom or whatever, like helium versus argon, it's got a higher velocity too. So it's going to have a higher kinetic energy.
Do you also want like more vibrational modes, like if they're achievable, or no, because they're usually way up there in like temperature?
That I don't know. I'd have to get into the equations and to answer that question. So I'm not sure on that one. Yeah. I know that we use superheated steam, way hotter than 373, but I still don't think it's hot enough to take advantage of the vibrational modes. You know, there may be 5% in that partition function, you know, a few molecules that are excited, but I think it's still just translation and rotation that we're getting all of the energy storage in. You know, it seems funny, the steam engine is something from the Industrial Revolution, right, 1800s, but we still base our economy on steam engines. All of our power plants are blowing steam on a rotor. So we still have steam electricity. It's just in a very efficient form. It's only 46% efficient, but it's still, you know, as efficient as we've gotten it to date. So it's kind of interesting. You would think that steam engines aren't used anymore, but all our power plants, even nuclear power plants, are based on steam. They superheat the steam, spin a turbine, and that spins a generator to make electricity. Well, I should say not all of them are steam. These new methane turbines, so it's essentially a jet engine, like a fighter jet engine that they burn methane in. And so then they're just running a jet engine on methane and spinning a generator with that. And so it's not steam, but it's still a you know, kind of like steam. It's spinning a turbine and generating electricity.
So I'm guessing those aren't anywhere near the populace, because I think people complain about steam.
No, it's not bad. No. Well, it's all consumed. I mean, they're burning it. It's combusting. In fact, you drive by one every time you go to College Station at Roans Prairie. So that's what that power plant is. It's a strange shape. You don't see any coal nearby or anything like that. And so you're like, what are they using for energy source? It's natural gas. So there's a natural gas pipeline that goes to Roans Prairie Power Station, and they've got 3 units there that generate like 500 megawatts of power. Yeah. It's nice because, well, we'll get into that. That's the 5th part of the course. So obviously I could go on, and I will. All right. So let's go back to this, focus on why we need those adiabatic relationships. Remember, we might have something like the displacement or compression ratio given to us in the engine specs. And so if we start with these things down here, the compression ratio is VC over VA. So it's the largest volume over the smallest volume. And you can get the compression ratio higher if you make the smallest volume really small. And so those cylinders in an automobile engine come right up close to the top of the piston chamber. Because the smaller you make that smallest volume, the higher the compression ratio. And that's going to be a higher efficiency. That's why in older cars, if you ever had a valve fall down into the engine, that piston could hit that valve and launch it through the hood. It'll come out of the head, through the head gasket, and out the hood. If you're, drag racing, like my dad used to do as a kid. He's like, somebody would lose a valve and they'd have a hole in the hood, and then it just totally launched it out of the engine. So that's the compression ratio. And then you have the displacement, which is the difference in VC and VA. Well, these numbers are given, RC and delta V, and so you've got two equations and two unknowns. And then like on the next slide, we'll derive how to get VA and VC if you're given compression ratio and displacement. So you will know these here and here, and then you will have to guess or estimate what the cold and hot temperatures are. And I think that's where my largest unknown is. In an automobile engine, what is the temperature of the cold and the hot? What's the range of temperatures we have here? And that I don't know, and I don't really have a good way. It's not the engine coolants. That's 210 Fahrenheit, whatever. If you add that up, that's not hot enough. I think the exhaust gases that are coming out are probably the best estimate of the cold temperature, and I don't have a good way to measure that. So I really don't know on an automobile engine what T cold and T hot are. If anybody wants to do some research on that on the internet, maybe you could find that out for us and share with the class. That'll be worth 2 stickers. So, but once you find the T hot and T cold, then you've got the Sudoku puzzle ready to go. You can use those two numbers to get the pressure at C. You can use the hot number in VA to get the pressure at A. And then you've got to figure out what VB and VC are to get PB and PD. VD and VB. So that's where you use those adiabatic relationships in filling out the state variables table. And in this case, I've got T hot and T cold, and I can use those with my gamma to find out VB. And the same thing down here. Notice that this is the adiabatic compression. Here, D is connected to A. D and A are connected by an adiabat. And so that's the temperatures and the volumes that you use to fill out this square. That's a number one mistake I see. People think, okay, I know how to use the adiabatic relationships, but they use the wrong temperatures and they use the wrong volumes in these ratios. Okay. So if you were to use VC, it would not work because VC and VD are connected by an isotherm. So it's VD and VA that are connected by an adiabat. And then figuring out B, VB is connected to VC with an adiabatic expansion. And so you would use the temperature at C and the temperature at B and the volume at C to find out the volume of B. And I've got some practice problems on Blackboard for you for that. So here's our, this was on a Trans Am calculator if you wanted to figure out how much horsepower you could get by boring out your cylinders and putting in new pistons and rings. And so this has, the stock amounts and the new bore. And so you've got displacement and compression ratio given here. So if you have those two numbers, displacement and compression ratio, you could solve for VC up here. So VC is equal to VA times RC. And then you can put this piece into that displacement equation and then solve for VA. Okay, and so VA is delta V, which is the displacement, divided by the compression ratio minus 1. And then once you have VA, then you can put that into this equation up here and then solve for VC. So that's displacement minus displacement over compression ratio minus 1. So those two equations will let you turn a displacement number and a compression ratio into your A and C volumes. And then once you have the temperatures, you can fill out the whole state variables table. And so that's it. Next time we will go through and do all the equations. We'll solve the state variables table and the performance parameters for a Carnot cycle.